Hello everyone, I'm Ryan, your host, and this is Transfer Processes 311. So far we have covered two main transfer processes, namely mass transfer, which pertains to the conservation of uh, Hello everyone, I'm Ryan, your host, and this is Transfer Processes 311. So far we have covered two main transfer processes, namely mass transfer pertaining to the conservation of mass and energy transfer pertaining to the conservation of energy. In today's lecture we are going to go on with our analysis of energy transfer, but focus more specifically on the rate at which energy transfer takes place. So without further delay, let's jump straight into the fundamentals of heat transfer. In the study theme, we will introduce the three modes of heat transfer that takes place, namely conduction, convection, and radiation. We will of course apply our knowledge by learning how to solve basic problems for each of the modes of heat transfer and also combinations of these modes. We'll also analyze systems characterized by a combination of these mechanisms of heat transfer. So let's begin with an introduction to heat transfer. Consider the following two control volumes containing matter A and matter B. Let us assume that matter A is at a very high temperature and that matter B is at a very low temperature. But what exactly do we mean by temperature? What is temperature? Well, think about how temperature is measured. There are many ways in which to measure temperature. We could use thermocouples, for instance, which are typical in industry, but one may be very well familiar with using a thermometer. A typical thermometer houses a working fluid, such as mercury, or in this case shown here, a thermometer containing ethanol. If we were to place this thermometer into the void of space, far from any matter or light, the volume of ethanol would shrink completely, such that the volume would be very small. We associate this very small volume with an equally small temperature reading, perhaps close to 0 Kelvin. What if we were to submerge this thermometer instead into matter A? The volume of ethanol would become quite large, corresponding to a high temperature, say for instance 1000 Kelvin. And when we place a thermometer into matter B, we obtain a lower temperature reading, say 200 Kelvin, based on the lower volume that the ethanol is now taking up. How did we change the volume of ethanol? Well, by adding or removing energy from the ethanol, or in other words, by transferring energy to and away from the ethanol. The addition of energy, for instance, results in an increase in the energy contained within the ethanol. What form does this energy take on then? In this case, kinetic energy, for instance, plays a very big role in the volume in which the particles take up, where particles of ethanol bump more frequently into each other. Each particle in the control volume takes up this energy according to its capacity to do so. And one form in which this energy is expressed is through kinetic energy, resulting in the motion and collisions observed within the control volume. We can go on to say that each control volume has an energy density associated with it. Matter A, for example, whose temperature is higher than matter B's, also has a higher energy density. In other words, energy is much more concentrated for matter A compared to matter B. Now, because of this higher concentration of energy for matter A, we observed the tendency of energy to want to flow out of matter A towards matter B, such that by entropy, the energy overall is diluted. Now we can ask, how is this energy transferred exactly? One way energy can be transferred is via radiation. Recall that radiation is made up of wave fields we denote as photons. What in matter is the main carrier for photons? It happens to be the electron. Electrons are continuously becoming excited and falling back or reverting back to their ground states. And by so doing, they release photons. And this is the form in which energy is transferred at this atomic scale. So this happens to be a conserved form of energy. Of course, all energy is conserved within the universe. And what happens when light is transferred between electron to another electron? Well, we have some, we can say kinetic energy, internal energy, that is taken up by other atoms next to these atoms that have just given off their energy. So let's follow this light wave or photon packet as it hits an electron. This electron absorbs the quantity or quantum of energy. It becomes itself excited, and then it drops down again and it releases this small amount of energy. This energy can travel through matter A, and eventually it can escape at the surface of matter A, where it is given off, or the energy is given off as a pocket of light, and this light will then hit or bombard matter that is in the vicinity. So in this case, we transfer energy as radiation to matter B. The next form of heat transfer takes place in what we call convection. Convection is all about movement or motion of matter. So you can imagine that matter A is a stationary or solid piece of matter, and matter B could be air molecules or water, something fluid that can flow past the surface. And specifically, convective energy transfer is always a motion of a medium past another. Energy transfer can also be via conduction. And what we mean by conduction is that both matter A and matter B are more or less stationary. Now, a gas and a liquid can also be stationary if we inhibit the movement of the liquid so much that the convection part of heat transfer is not realized or becomes negligible. So think of a droplet on your skin. That droplet is not going to go anywhere, and it is typically heating up via conduction. But if you blow some air past your face, that air takes up some of the heat. Maybe it's a hot day and you're also sweating. So by convection, you also have the air taking up some of the moisture from your skin, and that moist air then leaves the vicinity of your skin and goes off to somewhere else. So that is convection. Now, conduction is where the drop of water is really sticking to your face. It's not going anywhere, and it's going to eventually take on close to the temperature that your skin is at. Some of the exercises that we are going to get into at a later stage when we look at steady state heat conduction is where we have another matter, let's say species C, that is trapped between matter A and matter B. In this case, matter A can be a pane of glass and matter B can be a pane of glass. And in between these two panes of glass, we have got an air pocket. And we say that this air pocket has such a small length going from matter A to matter B that convection cannot take place or is negligible, so that energy is only transferred via conduction. Eventually, when we start to conduct energy from matter A to matter B, let's say matter A is at 1000 Kelvin, matter B is at 50 Kelvin, then the energy will become depleted in matter A, such that matter A will eventually take on some average temperature, given here by the green color, and also matter B will take on this similar temperature. And eventually we will dilute the energy across all the control volumes for A, B, and C, that they all take on, let's say, some temperature 500 Kelvin on average. And when this takes place, there's no longer any energy transfer, or specifically net energy transfer. Remember, the particles are always colliding into each other, but the net energy transfer to the right-hand side is more or less the same as the net energy transfer on the left-hand side. So if we sum all the energy transfer, um, let's say directions in the system, it's going to equate to 0. Time for a quick quiz. An astronaut is in space for the first time and realizes how boring it is up there. The astronaut decides to conduct an experiment to solve a question that has long been debated on his Facebook feed. The question is as follows. If someone were to pee into the void of space, would their pee freeze over, remain a liquid, or vaporize completely? What do you think? For this question, consider the volume coefficient of expansion and decide what will happen. Will the urine become a solid immediately? Will it first become a gas? What will happen? Think about it and we'll return to this quiz at a later stage. Let's now talk about conduction specifically. Remember that each atom within these two control volumes has a certain amount of energy associated with it. Matter A, of course, has a higher energy than matter B. Now, how does heat conduction take place between matter A and matter B? It does so by two mechanisms. Firstly, heat may be conducted by delocalized electrons that are able to move around more freely within the matrix in question. This is usually the electrons present in d orbitals. Since valence electrons of metals are typically occupying d orbitals, the conduction of or conductivity of energy through metallic materials tends to be far higher than that of non-metallic substances. A second mechanism is obviously by vibrations and rotations of the molecules themselves. The molecules bump up against each other, and obviously matter A's molecules are much more vigorous and they will collide into other molecules next to them much more frequently than the colder species of matter B. Let's consider the second mechanism in more detail so that we might understand the association between temperature and kinetic energy better. On the left-hand side, the white particle moves rightwards until it collides with the first particle in its way, specifically the red particle. This red particle absorbs the energy from the white particle and proceeds, albeit more slowly, until it collides into a particle of the same species. The velocity of particle A is much higher than the velocity of particle B, and there is a direct or proportional relationship between the temperature and the kinetic energy for these particles. Because the white particle's velocity is much higher, it also has a higher kinetic energy, and therefore a higher temperature associated with it. Now let's consider that some time passes and these particles bump into each other back and forth, back and forth. Eventually they will reach an equilibrium where the white particle will take on the same or similar velocity as the red particle. And the red particle will of course be speeding up so that the velocity Vb is going to be some average between the starting or initial velocities when we first observed the system or this control volume. Although we can say the driving force for energy transfer from a hot body to a cold body is due to differences in kinetic energy at the atomic or even the subatomic level, we are more interested in describing heat transfer using measurable quantities at the macroscopic level. We therefore say that at the macroscopic level, heat is conducted due to a temperature gradient. The steeper this temperature gradient is, the greater the driving force for heat transfer. However, temperature alone is not the only deciding factor here, and you must remember this. The rate of heat transfer, where I say the rate, okay, so the speed at which heat is transferred, is also dependent on the properties of the material, and we will discuss this in more detail shortly. Now let's recall that heat transfer is much better for metals than non-metals because of the delocalized electrons of the d orbitals for the transition metals. Right. So to demonstrate this phenomenon, you can try this experiment at home. Place one of your hands onto a metal object, say a pot in your kitchen that is just sitting in the cupboard somewhere, and place your other hand simultaneously onto a wooden surface such as a breadboard. Which of these two items feels colder to you? Do you realize that both of these objects are likely to be at the same ambient temperature as the room in which you found them? So why does the metal object then feel colder to you than the wooden one if they are at the same temperature? What other properties other than temperature determine how energy is transferred from one object to another? So the driving force is the temperature gradient. If there wasn't a temperature gradient, then heat would not be transferred to begin with. However, there's another factor, and this factor we call a property of the material, specifically the thermal conductivity. How well does the metal conduct energy? Well, much better, because the electrons are more delocalized than the electrons within a wooden object, which is more insulative. So the thermal conductivity, or the ability for wooden objects to conduct their energy or to take energy into themselves from a hotter object, is inhibited by this property, thermal conductivity. So take a look at this equation. On the left-hand side, we have got the rate of heat transfer, Qx. Heat is being transferred in the x direction, and that is what the x subscript is for. The energy is being transferred through a specific area. So think about you placing your hand onto a wooden surface and the warmth of your hand being transferred out of the palm of your hand, which is the area, and into the area of the wooden object which your hand is currently covering. Notice that the direction of heat transfer is perpendicular to the area through which heat transfer is taking place. This is the area which we are referring to here. On the right-hand side, we have got K, which refers to the thermal conductivity of the material. It is a material property. It is typically a function of temperature, but it also depends on the type of material we are talking about, whether it be a gas, a liquid, or a solid. And thermal conductivity is not always a strong function of temperature, as we will see later in an example. And lastly, the thermal conductivity is multiplied by the temperature gradient. So, in summary, on the left-hand side, we've got the rate of energy transfer per meter squared, and this refers to an energy flux if you check the units. K is the thermal conductivity, and we have the temperature gradient, which is the driving force. So, yes, this looks like a flux term, and you can compare this to the mass flux, which we did in the previous study themes. And you'll notice that the units for energy flux is joule per second per meter squared. So, to summarize, this relationship is referred to as Fourier's first law of heat conduction. The temperature is the driving force for this heat conduction, where K is a material property which also dictates the rate, or specifically how quickly this heat is going to be conducted. Let's take a look at thermal conductivity in more detail. A derivation for the thermal conductivity for gases is provided in a textbook, and the resulting equation is shown here. It is possible to simplify this further into an easy-to-use equation where only the temperature, molecular mass, and other properties of the gas is required. These properties, specifically the force constant and the collision integral, are also available in appendices at the back of the textbook. Typical thermal conductivities for liquids and solids are also available, either as equations or graphically. Fortunately for us, since temperature gradients dealt with in industry are not that large to begin with, The thermal conductivity may be estimated by some linear equation, but more often than not, an average is simply taken without any issue. Now, have a look at these two graphs. Let's look at the thermal conductivity for liquids, for example. Take CO2 at the bottom. Let's say the temperature varies between 100 and 200 degrees. It is apparent that a linear correlation could be used to estimate the thermal conductivity, but look on the right-hand side and see that the thermal conductivity does not vary all that much, and so we would actually just be splitting hairs. So why not just take the average of the thermal conductivity between these 2 points? The same goes for the thermal conductivity of solids, and you can notice that the gradients for the thermal conductivity are not really that steep, and so taking averages or linear approximations is also acceptable. Notice the units of thermal conductivity. W, which stands for watt, is joule per second, and so the thermal conductivity actually dictates the rate at which heat is transferred. So remember what I said before, even though we've got a temperature gradient and we require this for heat transfer to take place, we also need the thermal conductivity to know what rate or how quickly this heat will be transferred due to this temperature gradient. So now that we've completed the fundamentals of heat transfer via conduction, we can move on to describing the principle of heat transfer via the mode of convection. Recall that convection takes place when a fluid, either as a liquid or gas, moves past a solid surface. When this movement takes place as a result of the natural differences between the density of the fluid at different positions in space, we call this mode of convection natural convection. If we were instead to force the fluid to flow past the solid surface instead, let's say by setting up a fan close to the surface, we would then refer to this mode of convection as forced convection. So think of yourself on a hot day. You would prefer to fan yourself with a piece of paper to help you cool off, rather than to just sit there and allow natural convection to take place, because you won't cool off as quickly. Now, what does the equation look like that describes convection? It looks similar to the form of equation that is used to describe heat transfer via conduction. And this equation is referred to Newton's rate equation. Note the H. The H is the convective heat transfer coefficient. So, when we have natural convection and air is the fluid in question, the convective heat transfer coefficient can take on various values between 5 and 50 watt per meter squared Kelvin. And so you can realize that the convective heat transfer coefficient is a function of the velocity of the fluid. Note the difference in units here compared to thermal conductivity. And beware, thermal conductivity's units are watt per meter Kelvin. If I force the air past the contact surface, then the heat transfer coefficient takes on much higher values. If I'm using a liquid, for example, these values will be higher still. We can also make the following distinction, where we could say that we are measuring a heat transfer coefficient at a specific place on the surface of the contact surface. And we can, of course, integrate this. So we also have a small area, and then we integrate the energy coming from the small area that has a specific heat transfer coefficient associated to it, and on integration we get the overall heat transfer that is applied across the entire surface area. Again, remember, the heat transfer direction is perpendicular or normal to the area from which heat is being transferred. Lastly, we can talk about heat being transferred via radiation. This is a very special form of heat transfer. The previous or initial heat transfer modes that we've discussed, specifically conduction and convection. These two modes or mechanisms of heat transfer require matter to be present, either a contact between two solids or contact between a solid and a moving fluid. Radiation does not need a medium in order for energy to be transferred. Photons or radiation can be transferred in a vacuum, and so you must realize the difference here. We describe radiation heat transfer using the following equation, where sigma represents the Stefan Boltzmann constant, which takes on a value of 5.676 times 10 to the negative 8, and note the unit, watt per meter squared. You can read up about radiation in more detail either in the textbook or online. We will return to radiation specifically when we complete some of the tutorial questions, but for now, let us discuss the more important combinations of the three mechanisms, or modes of heat transfer. Heat transfer almost always involves either a combination of two or three of the modes of heat transfer. Most often, it is a combination of conduction and convection. But when we deal with high enough temperatures, radiation begins to play a significant role too. Therefore, when completing problems pertaining to these mechanisms, a full in-depth analysis is necessary, and reasonable assumptions once again need to be applied. First and foremost, with regards to conduction, we will start off looking at steady-state conduction. We specifically look at energy, specifically heat transfer, proceeding in the x direction. And the following integration that I've laid out in the slide here applies. When we complete the integration, we get the following simplification of our equation. And note that dx has now taken on a value or quantity length L. Let's consider now the following system. In the first analysis, we focus our attention on the hot air. The heat that the air contains is transferred to species A via convection. What is then obtained is a new temperature against the surface of A and the air, T1. The temperature difference here is TH minus T1, and this is equal to the heat that is being transferred, Q, in the x direction, times by 1 over the convective heat transfer coefficient for the hot air, H subscript H, and the area that the hot air is falling on. The next temperature gradient, you'll notice, is linear, going from T1 to T2. This is also equal to the same heat transfer, Q, in the x direction. And take note now that because we are operating at steady state, the two equations have the same quantity for Qx. And if we were to, for example, divide the two equations by each other, Qx will simply fall away. The same will occur for the area because we are conducting and convecting this energy through the same meter squared area. Thirdly, we have another temperature, T3, where B and C have a boundary that they share. So the following equation, again, is for conduction that occurs from surface AB to surface BC. And the next one is from surface BC to where C contacts the air, forming a new temperature, T4. And lastly, we have convection from T4 to Tc. Now that we have all our equations, what we can simply do is add them together. If we add the first to the second, notice that T1 is common except that there's a sign difference, and so T1 will cancel out in equation 1 and equation 2. If we add this summation to the next equation, T2 minus T3, we will then cancel T2. And likewise for the next equation, right to the last equation. What we will end up with is simply T hot minus T cold, which is equal to the heat being transferred straight across the entire control volume multiplied by all the uh, convective heat transfer coefficients and thermal conductivities, specifically the reciprocals of these. We can rewrite this equation to have Qx on the one side equal to the temperature difference divided by the sum of the reciprocals of the heat transfer coefficients, thermal conductivities, and their multiplication with the area. Notice again that this is the same area. These reciprocals multiplied by the area represent a resistance. And so the heat transfer through this control volume is equal to the temperature difference divided by the resistances. So look at the analogy that I present here. The current is reminiscent of heat transfer. The temperature difference is the potential, the driving force for heat transfer to take place, and this is reminiscent of a voltage difference. And lastly, the sum of the resistances is reminiscent of the resistances in an electric circuit. Later on, specifically next semester, when we continue with chemical engineering design, specifically of heat exchangers, we will come to a concept called the overall heat transfer coefficient. Its definition is equal to the heat transfer divided by the area times by this potential difference, the delta T. Now that we've completed the fundamentals of heat transfer, we can continue with some exercises.